Okay, so I want to keep on going on with the particle in a box. So we go that little well. So we have potential like this for B. This is for X. How did our potential look? Okay, so we have this going off here. This is B. We call this region. Here is going to be 0. And we call that L. And up here, that goes off to then be here like that. We're taking energy of the system like that. And that was region 1. This is region 2. And this is region 3. We solved the Schrodinger equation in each of those regions. Yep. And so what we found in here in region 3 is we had, okay, what we're going C1?
Sure. I don't remember.
I like to give the same notation as possible.
C1.
C1? This is C1 e to the beta x. Is this coming into the beta?
Yeah, yes.
Okay. Then C2 e to the minus beta x. We have that. And this is going to be true for this region here. But there's a problem with that. What was on the problem?
1 section.
Yeah, the beta is positive. And what does x go in this region? It goes from L to off to infinity. And so this term here is actually going to blow up exponentially. And since that's not physical, you have to have the C1 equaling 0. So this is C1 equals 0, since e to the beta x goes off to infinity as x goes off to infinity. So what we end up over here, in side 3, we end up with just this function. Okay. And side 2 here, okay, this one, what were our C values? C.
Think of 6, 7.
6 and 7?
5 and 6. Sorry.
5 and 6. In terms of the sine and cosine. 6 and 7?
6 and 7.
We had C6. Cosine. This is 7A?
C5, C6.
In terms of the cosine.
Cosine kx. C7 cosine kx plus C8 sine kx.
Sine of kx. And that one. Okay, would anything go off to infinity in that region?
Nothing. It's also
Nothing. This is offsetting here, and not only that, the region is finite as well. So nothing can go off. This region inside 1 is that it looks exactly like this one here. Some very different coefficients. There were 3 and 4. So I think we had C3 e to the beta x, C4 e to the minus beta x. And in this region right here, which of those is well behaved?
The
C3 ones. And here's the way, how come?
Because negative.
So the beta is still positive, but in this region here, the x is negative. What happens here is that the C4 has to be 0, e to the minus beta x goes off to infinity as x goes to minus infinity. That makes sense? So our C1 was just this guy here. So we had this guy, this fellow, then we had this fellow. Okay, so everyone happy with that? And we said if we drew these things, if we drew our psi versus x, we could have a lot of different looking things here. I could have something like here, so this right here would be my x, this is my L. I could have something like this. That'd be a perfectly fine one to have. Okay. We also have another one too. We also have one that goes like that. That's also a perfectly good one to have.
That's when you there is like a finite amount of possibility.
In this case, yes.
Right? Or is this those two?
You would have to know what the energy is, and you have to know the height of the well, and all kinds of. You can actually prove that you can always have a minimum of 1. You can never make a well so shallow that you can't handle this one excites. I mean, one. That's not for this course. Okay, so we have things like that. Now we're going to give these different names here, but I want to set up the boundary conditions here. Now, what were our boundary conditions on psi? We said one is that psi has to be finite, and so that got rid of here and here. But what were our other two conditions on this?
That we never did it be continuous at the boundaries.
And side stuff has become continuous. So there's actually two boundary conditions here. Boundary conditions on psi. One is that psi 1 at some value, I'll just say at some value L, that's equals psi 2 at L. The boundaries are occurring at L here. And the other one is that the derivative of this. So L has to equal the derivative of this at that same plane. So let's actually set this up for this problem. So in this case here, what would be the boundary? Let's do this one here. So, phi boundary conditions. Okay, let's do this one first. What would they become? What would be the boundary conditions for that?
Like this, side 1 equals side 2.
Just we have the psi 1 at where?
At 0.
At 0.
Must equals side 2 at 0.
Psi 2 at 0. And what else would we have?
Side 2 at L must equal side 3 at L.
Exactly. So what would that become in this case? What do we have? What is there, psi 1? So if we evaluate this at 0, we get
C3.
C3. Here's my buddy psi 2. If I evaluate that, x equals 0, I end up with
C7.
just the C7 this turns out. Equals C7. Woohoo, one equation. Got one other, yes.
When you're drawing like the continuous curves like that, is that psi or is that the like psi squared?
Can't be psi squared from one. Okay, this one you couldn't tell. Tell me why you can tell with this one.
Because the negative torque.
Yeah, this would actually have to be flipped up. Okay. Now, what does this one do?
Well, there's a bell. Just replace x by L. I mean,
And so you're going to have
C2
C7
plus 7 cosine of
cosine K
L.
L plus
C8 cosine of L.
C8 sine K L equals.
C2 e to the minus beta L.
And here's my sine 3. So this has to be C2 e to the minus beta L. What do you think the most common mistake is when people do that condition? They just have an X here, an X here, and an X here. Why is that fundamentally wrong? Where does a boundary condition apply?
At the boundary.
At a boundary. If you just have a generic X there, what are you saying? You're saying over a whole range. So you always have to evaluate this actually at the boundary. Okay. Let's do another one. Let's do this guy. So what does our derivative equation become? It becomes this. Partial psi 1 and x equals 0. Evaluate x equals 0. Has to equal this guy here. And then we have the partial psi 2 at L. Has to equal the partial psi 3. Also L. So what does this give you? So do so. And what do you end up with?
Beta 33 e to the beta x.
Yeah, so the derivative of this is going to be beta C3 e to the beta x. But evaluate this as x equals 0 gives me
Beta C3.
beta C3. Here's my buddy C2.
Well, K, no, minus K7 sine of KX plus K8 cosine of KX.
Evaluate that at x equals 0. What do you end up with?
K, KC8.
The KC8 curve. The other one I'll give B0. So this will become KC8. Boom. Okay. Buddy over here, what does this one give us?
Complicated expression because it's L, so I'm not doing it.
Okay, it'd be the same thing you said before to just put an x equals L. So what Junior says, we'll write that down. This is minus K C7 sine KL plus K C8 cosine KL equals what?
Equal minus beta C2 e to the beta L.
Exactly.
Minus beta.
So minus beta C7, I'm sorry, C2. E to the minus beta L. Boom. So how many, in our wave function here, how many unknowns do we have?
We have, wait, in Python?
In this wave function here?
We have
How many unknowns do we have?
all the constants, but one.
I haven't agreed there's 4?
And
Tell me why there's 5.
I think.
It's a subtlety here. I mean, you could look and say, well, 1, 2, 3, 4. 4 looks like a perfectly good answer.
Yeah.
But why is there 5?
You know,
K is beta.
Okay, what do both K and beta depend upon? E, the V is fixed, but the E is, we don't know what the E is. So E would actually be our 5th unknown. So when you're wee little, like K big, and you're in high school and you had on your little beanie, you know, your little hat, your beanie propeller like this, and you had your little sock monkey, you're in algebra. What did you find out about equations solving them? You need as many equations as
Many unknown.
you have unknowns. Okay? How many equations do we have here?
1, 2, 4.
If I wanted to find all these coefficients, all the term constants here, where is our 5th equation? So I need to write that down. So it's all right down. I think we can kill the picture here. We'll do a match, right? So there are 5 unknowns in our psi. They are, let's see, C3, C7, C8, C2, and E. Boundary conditions give us 4 equations. Question is, where is the remaining equation? It's in Hornell. No, where else? Is there another constraint we like to put on psi? Is there a constraint on psi that we know and love? How do we interpret psi?
Psi squared plus half 1.
Take psi squared and integrate it over all space 1. So we have this one here. That's our remaining equation. Let's write it for this because it's going to look really, really weird. Okay, this is going to be kind of bad news, but then we're going to.
Is it the absolute value or is it the magnitude?
It's that notation means what? That's the notation used in math. Absolutely doesn't mean.
Times the complex.
Yeah, this right here, when you have this right here. By definition, that's just. So how would you write it in this case here?
Right. Oh, what is?
We have to integrate our psi over all space. Hey, how do we do that?
We first need to write the general side.
Oh, I can't wait to find out. Because we're going to do our solution here. I'll start off by writing this over here. Our wave function was this. Okay. That's we had something that was one example.
The linear combination.
Tell me how to do that.
Combine
Tell me how to do that. Tell me what to write.
the side general equal steep side one.
So tell me what to write here.
Yeah, I don't know, C8 side one plus C9 side
Integral
two.
from negative infinity to 0.
Good. Going from minus infinity to 0. And in that region there, what's our wave function? There's our friend
Side one.
psi 1. Keep going.
0 to L side two.
0 to L. Psi 2.
Then from L to plus infinity.
L to plus infinity, psi 3, grid dx 1. This is our other equation. Now, so you have 5 equations, 5 unknowns, you solve them for everything. You look at that and go, oh. Okay, now here's the good news. The good news is this is rarely do you do this part here when you do these. Normally, just from the boundary conditions, if you're tinker with them, you can come up with what you really worry about here is almost always the energy. And so it turns out to be a lot easier. You normally don't have like, 4 equations, 5 equations, 5 unknowns. It usually comes down to something a lot easier. Okay. Because you often want to get what you're often interested in is that eigenvalue, that energy eigenvalue. Okay. So if you look at, does anyone have the homework with me? Okay. I mean,
Which one?
okay. The daily, the actual homework 4. Okay. Is that homework 4? Oh, no, not homework 4. Okay. So in homework 4, if you look at number 3, and let's look at number 3. Actually, let me do one more thing now. We'll go. What would then be this? Let's ask for this problem.
Average of something.
It's the expectation value. Hey, it's almost like maybe there was a postulate.
Yeah.
Okay. What do we know about the postulate for this? These are given by any expectation value of any quantity, some quantity O, is what? Integral from minus n over all space.
The complex conjugate of psi
Psi star.
times value
Well, the operator, whatever that is,
times the psi.
psi dx. What would that become in this problem here? So in this problem here, I want to do this. The word the Scooby-Doo, this would be. Haven't I taught you guys how to speak Scooby-Doo? I teach so many people how to speak Scooby-Doo.
What is that speak? We don't know what's that.
Okay. Okay, you just put a lot of R's to things.
Oh, okay.
So it'd be ring, ring, Reggie. Which is same thing, Shaggy. Okay, ring, ring, Reggie. Okay, so tell me what to do if you do ring. We have an integral going from minus infinity to 0.
Oh,
Side 1 star, and it's just gonna be, it's gonna be just, it's the same thing as side 1, in this case, it's real, so we don't, but I wanna write it like this. X side 1 dx plus
yeah.
0 to L,
Thanks for X.
2 star X side 2 dx plus
Oh, infinity.
of the side 3. I'm gonna give you a hint. Homework 4, question 3. On question 3, that's my wave function. Now I want you to find n where let's start off with n. What would be a good name for n? That value of n is often called a constant.
Constant.
A normalization constant. Why might we call n here a normalization constant?
Two on side 0, 1.
Is there any constraint? Think about what we've just done here on this side. For interpretation for psi.
That's probability of finding a particle in that space.
What does that mean?
Has to equal 1 or something.
Put in some details there. There's not enough math in there. So your psi star dx is a probability of finding the particle between x and x plus dx. Ergo, in the terms of Scooby-Doo, Raro, that's Scooby-Doo speaking Latin. You have to take this wave function and integrate, square it, integrate it over all space and set it to 1 and figure out what that would have to be. So how do you do this in this case?
Integral from negative infinity to 0.
So we have, you know that this is a case. That have the integral from minus infinity to 0. And what would be your wave function in that region? That's 0 because of this right here. This would be 0 dx, so that is just does nothing. There you have 0 to infinity of this n times x e to the minus x squared dx. And that you would solve set to 1. Okay. At some point, I'll show you the magic way to write down that answer. Private conversation between Dominic and I. Dominic, if you recognize what that is, you can do the nice fancy way. Okay, the others don't know that yet, so they cannot.
I don't think I recognize that.
Okay. If you think about it, you know what to do.
I will.
These are my class course where we've talked about this in type of material. Sure we have. Okay, so that's what you do there. Now, what would you then do with these guys here? How do you find X? Hey, these are expectation values. Is there a way of finding expectation values of quantity? This fellow's gonna have to be what? Integral from minus infinity to infinity of psi star x psi dx. What does that become in this case? What happens from minus infinity to zero? Zero. The wave function is zero, so that doesn't count. So you're going to get an integral going from 0 to infinity of this n x e to the minus x. That's my psi star. We take n to be real.
Is that squared? This would be on the side.
And x, then this, which is going to be just something with the psi squared.
And it's just because we only have real components.
That makes sense? What are you gonna do with this one here? You're gonna really like integration by parts of this one here. Why don't you do some integration by parts review, which is what I'm not telling you the beautiful way of doing this. You can actually look at those integrals and immediately with the answer. But you're not there yet. Someday you will. What's that? I agree, okay?
The integral from minus infinity to infinity.
Integral from minus infinity to infinity. Psi star. What has to go here?
Yes, but not the,
Px hat, which is what?
which is minus
Minus I
h bar
h bar.
partial of something partial.
Partial with respect to x. And then the psi has to then be here
Yeah, no,
with the dx.
oh, yes,
So you have to take the partial of psi with respect to x. Okay, and then proceed to do this. Okay. You might want to do these with a buddy just so you can check your control for each step. Because there's going to be there will be now. There will be a map in this. Okay. That makes sense? Questions? Okay. I want to talk about why we even care about this model here. This seems kind of stupid. Then I want to show you we're going to do actually a simplification on it, which we're going to put up knowledge out of. When we are done with all this stuff, not quite yet, but we have to kind of do the 3D version of it. We will find out why works work and why neutron stars work. It turns out that there's actually something quite subtle about that occurred. That, for instance, if you increase the mass of a white dwarf, what does it do? It actually gets smaller, which sounds preposterous. You know, because if it gets bigger, you'd expect it to get, it becomes more massive, you expect it to get bigger. It actually gets smaller.
then they just
There's a reason why.
like fall into their own gravitational.
No, because something's going to happen. It's going to be entirely connected with the spots that you're going to be able to understand. Okay. So why do we care? With finite, finite 1D potential well. The problem we're doing is called the finite 1D potential well. The answer is going to be that it's actually going to be an approximation to a one-dimensional wire, an electron moving in a one-dimensional wire. So the answer is the 1D finite well is a model for an electron moving in a 1D wire I'm going to show you how this works. So let's say I have a wire here, has a length L. I have one little electron here, and that little electron can move back and forth. We can model that electron as that finite well. I want to show you why. For those of you who know a little bit more about condensed matter physics or solid state physics, depending on what you want to call it, this is going to be an example of what is referred to as the free electron theory of metals. That word may mean something to you, it may not. We're going to head. I want to show you how the free electron theory of metals work. Let's go through stuff. Okay, so let's do a little review. So this is plus Z. If this is my nucleus, if here's my electron here, this is R. What is the potential energy for this?
Q or K, Q1, Q2.
K, Q1, Q2. If I were to graph this, let's say here's my little Z. Okay, what would that look like? Well, that would be something that looks like that. Okay. Now, what can I view this wire as being made up of? I can view this wire as being made up of a whole bunch of atoms. I can say the wire here like this L. What this really is a whole bunch of atoms like this. So the wire made up series so let's kind of look at it individually. Let's look at the potential for an electron interacting with each of those electrons individually, each of those atoms individually. Plot V here. And imagine I have all these nuclei. These are all the, I'm going to put a little more space here. So on and so forth. And so let's neglect all these electrons, all these atoms here, and let's just consider this one here. How would the voltage, how would the potential energy look just for this fellow here? Well, actually, it'd go like this. This is just for this one here. And if I were to extend it out like this, let's say there's no atoms here, the potential would also go out like this. This is just for this one here. Now, neglect this one, this one, this one, neglect all of them except for this one here. How would the potential energy look for an electron just interacting with this if I neglected everything else? Well, it's going to look just like this, but it's just going to be shifted. So I'm going to draw like a little dotted line here. This is going to be kind of like a new axis. For this one right here, I would just have something like this, and then something like this. Okay. Now, what would happen if I neglected this, this, and only considered this guy? What would I then have? I'd then have this guy, and then have this guy. And I could do this so on and so forth for all these here. If you add those on, then if I do the last guy, this one and this one. We should actually look at what this looks like. you'd end up with something that looks like, I put little lines in this. You'd end up with something like that. Yep,
It's just like the chronic penny model.
you can, that's a specific model, but it actually that ends up being the chronic penny model. With that, you use that basically to get the block wave function. We're not gonna do the block wave function in this course. That's even for me beyond the scope of this.
Okay. But then it like was written like this, but then it was like a simplification of that.
Now, we want a simple model for this. What can we say this is, crudely speaking? If I want to be crude on this, what I could say, that's all this is. This. I could say it's that. It's crude, but I don't care. I want a simple model. Okay. Hey, what is this? This is our finite well. This right here, this is a finite well. A 1D finite well. Okay. So that's how that works. That's why we're considering this, because it actually shows up quite a bit. Okay. Make sense? Now, yes,
What are we talking about when we say well?
that's right here. It's just potential energy versus distance. So what we have in this case here, we have this guy, potential energy here. And we're assuming that the electron is here. That we're assuming the energy here. So the electron is kind of trapped in this tree. So we call it a well. Okay. Now, with that said, let's actually do an even more crude approximation that we can then solve exactly. Let's assume something even easier. We're going to use the infinite 1D well. What do you think the infinite 1D well is going to be? Well, the subtle V here is going to be infinite. So we're going to take this, send it off to infinity, take this, send it off to infinity. So what we're going to have is this. Instead of having this. In the Latin, V go off to infinity. And have something that looks like this. This means off to infinity. We're going to do that for one. The reason why we're going to do it is we can actually solve them exactly. Okay. So let's go through and see what we get. So we have these regions here. 1, 2, 3. What do we say side is? This is C2. This is C2 e to the minus beta. And we graph this thing. We had something like, we had that. Okay. This is for the finite well. Now, what happens if our V goes off to infinity?
Our equations go from in as well.
No. What did we say these betas are?
Hold up.
Remember these? Remember how we had beta squared? Was this 2m h bar squared b minus c? Okay. So our beta is this guy. Well, what does that become if our potential goes to infinity? Beta goes to positive infinity. So as V goes to plus infinity, beta goes to plus infinity. Hey, what happens to my region psi 2 then? I mean, the psi 3,
These shrunk down.
it goes to 0. So what that means here is that my psi 3, which is this. Okay. So my beta is going off to infinity here. This goes to psi 3. Equals 0. That's kind of neat. Okay. What about this region over here? My side 1. And what was that? C3? I think it was C3, right? It's this guy. Now, what do we know about this x here? This x in this region is negative. So beta goes off to positive infinity. This x, even if it's a little negative, what happens then? That goes, so it goes to 0 as well. So our side 1 is 0. So what does our wave function look like? Zero here, 0 here.
Whatever loopiness does, just in the middle there. Yeah.
We have that. Okay. This becomes important. Let's see what happens. So our psi in this region here, right? Our psi 1 is 0. Psi 3 is 0. What did we say psi 2 is? B7 cosine of kx plus C8 sine of kx. Okay, we're gonna have some magic occurring here. Get ready. Okay. At x equals 0, what's a psi 2 have to equal? How come? So the psi to be continuous. So we know that psi 1 at 0 has to equal psi 2. 0. Okay, so what does this equal? This is 0. This is C7 cosine of 0 plus C8 sine of 0.
So it's going to be 0.
Yes, so this goes off to 0. Cosine of 0 is 1. This tells me, boom. Hey, what's my wave function now become in that region? Just a sine curve. So now what happens here is that this gives us psi 2 at x. I will say psi 2. We lost that fellow. So this is C8 sine x. Hang on, we have more going on here. Is there another condition that we know about psi 2?
Also has to be equal to sine 3 at L.
At L. So we know that psi 2 at L has to equal psi 3 at L. So this has to be psi C8 sine KL equals 0. When is a sine function equal to 0?
Its side of the sine function is over 90 degrees.
Okay. More?
Higher.
Can you say 90 degrees? Is the sine 90 degrees 0?
Not that, no.
I agree.
When it's equal to 356 degrees. So an angle of 2 pi.
Okay. Does it have to be an integer of 2 pi? You said 2 pi. It is 0. Other values? Pi. Pi? Other values?
-5.
Zero.
Hold off on the minus ones. You'll see why.
0.
I'm gonna hold off on 0, you're gonna see why.
Yeah.
So pi, 2 pi, 3 pi, 4 pi. In general, when is this gonna be 0 here? And this argument here is n pi. So what does this tell me? This tells me that k, then pi over L. So our wave function here would be this constant here, the sine of n pi L x. Well, what do you know about k? Is k equal to anything special? Yes.
Good question.
These.
But squared is also
Square root of the square.
2m h bar squared
E minus E.
e minus b. What was b inside the box? Inside the box.
Oh, it was less than, no, it was big, no, it was bigger than 3. No, it was
Inside the box.
0.
0. Okay. So inside the box, b equals 0 inside the box. I got k squared equals 2m h bar squared e. My k squared is my buddy here. And I can solve that for e. Now we have a remarkable answer, very profound answer. I solve this for e. This gives me h bar squared over 2m. N pi over L squared. It's never written like that. It's always written as h bar squared pi squared n squared over 2m L squared. What does this energy depend upon? On the quantum number n. Okay. What happens here? We have a perfectly quantized system. Is that this right here is a quantum. It perfectly determines the energy level that we're in. Okay, now a couple of things here. I said that n can't be 0. Okay, why can n not be 0? The energy would be 0, and then this becomes a trivial solution. Okay, it's basically if n is equal to 0, what does it mean about psi?
0.
0. And so when you look at the Schrodinger equation like this, what's the trivial solution to this? The case where psi is 0. That's called the trivial solution. Okay. Now, why?
Energy will be negative.
Well,
No, I know what the question is.
okay. Why can't then the n be negative?
Because the energy will be negative.
It's all coming in squared here. Fine. Okay. What do we know about this k value here? Okay. This k value is actually going to be a positive one. Okay. And so what's going to happen here is that this n here is only going to be positive.
What is the meaning of the K value?
We haven't gone to that yet. So this is what we have. What would this look like if I graph it? I could have n equals 1. So this would be this value here, n equals 1. And this would be E1. So I'm going to put a little n down here. I'm going to have them match up. And this will be h bar squared, pi squared, over 2ml squared. Okay. Hey, what happens if n is 2? So this whole quantity here, that's really E1. So if my n is equal to 2, it sounds like you have a list, doesn't it? 4E1. 4E1, 1, 2. So this is going to be E2 here. So this is gonna be n equals 2. This is 41. I write it as 2 square root of 1, which is 41. And it sounds like you're saying 41, not correct, so it's really 4e1. What happens if n equals 3? What's happening to the spacing between these levels? It's actually increasing. So then you'd have this one up here, this would be then n equals 3. This is going to be e3, and this would be 3 squared e1. This would be 9e1. What's going to happen? They're going to keep on increasing like this. How do it look for the hydrogen atom? Do the energy levels go like this?
No, they're really giving.
They get crunched together. How did it go for the harmonic oscillator when you work that problem? They're evenly spaced. So how these energy level diagrams look, actually they vary from problem to problem. All the systems are going to have different energy level diagrams here. And these energies here, what are they? They're nothing but the eigenvalues of this problem. And this right here is our eigenvalue. Okay. So what we're going to do, we're going to tinker with this. And this is going to become a really good model for the metal. And the model that we're going to have for the metal is going to be called the free electron theory of metals. And actually that's going to work a lot better than it has any work to do. Okay, and then what we're going to do, we're going to tinker with that. Then I want to show you a band structure. Then we can talk about what it means to be a metal, what it means to be an insulator, what it means to be a semiconductor. Okay, then we'll apply this then to different things. I'll show you how we get a white dwarf. Tinker with that, show you how you get a neutron star. Tinker with that, show you how it applies to nuclear physics. Okay, it's all going to be variations of this. For this dumb little problem, you get a lot of knowledge on it. Have a great weekend.